The manifestations of light's electromagnetic waves is constrained at singularity points, like the manifestation of electrostatic fields in the theory of the electron. It can't be ruled out in such a theory that the entire energy of the electromagnetic field could be viewed as localized at these singularities, just like in the old theory of action at a distance. Einstein really wanted to get rid of Maxwell's equations, wanted to get rid of them, replace them with what we now call photons, but not photons that obeyed Maxwell's equations, photons that were different, really were little packets of energy with singular points telling them how to move and controlling their dynamics. Then in the small print he goes on to say that you could recover Maxwell's equations as an approximation if you had many, many of these points nicely spread out. In 1920, after formulating general relativity, Einstein embraced a space-time metric ether. General relativity is based on having a metric field that fills all space and time. That's really its primary hypothesis. Even then, though, he was a stubborn fellow, and he expressed doubts about the electromagnetic ether. More careful reflection teaches us, however, that the special theory of relativity does not compel us to deny ether. Then he goes on to say that for gravity you should have an ether, because it's impossible to even think about space and time that doesn't have a metric field. Which is wrong, by the way. You certainly can think about it, and we will. But then he goes on to still, even in 1920, be expressing doubts about whether there's an electromagnetic ether. Skipping ahead quite a bit, I'm going to tell something you don't know for sure. This is a personal anecdote about a conversation I had with Richard Feynman. Usually Feynman was performing. But one day we were at Santa Barbara. He had given a seminar. He got tired after a very busy day, people asking questions. Now I know how he feels. So he was tired, he relaxed, he wasn't performing so much. And he started reminiscing about, we had a wide-ranging discussion, he started sort of getting wistful about the past. And he told me about his early ambitions for his theory of electromagnetism. You know, but you have his Feynman graphs where you have particles instead of fields interacting with, exchanging other particles, so you don't really have fields, apparently. In the early days, Feynman thought that this was a different theory. He wasn't trying to make a different mathematical formalism for the existing theory. He thought this was a different theory. And his dream, or one of his motivations in doing this, was that he wanted space to be empty. The reason he wanted space to be empty, he explained to me, was that he was worried that if the field formulation were correct, with all the vacuum fluctuations you have in the fields, empty space should weigh a lot. Even back in the 1950s, Feynman was already worried about what we now call the cosmological constant problem, or the fact that vacuum energy is much smaller than it should be. And he thought that you should just empty it out. In fact, he told me in his Brooklyn accent, I can remember the exact words, and I'll try to reproduce the way he said it. He said, "I thought I could explain why empty space didn't weigh anything. It's because there's nothing there." Well, so much for history. In today's fundamental physics, space is full, but what fills it is different in many ways from the traditional ether concept. And as we go on, I'll compare with some of these historical concepts. So let me first discuss was something I already alluded to, that ether not only shouldn't be thought of as banned by special relativity, but in some sense is made inevitable by special relativity. This was already true in 1905, or why I found Einstein's statement so puzzling is that if you think more deeply about the situation in 1905, it wasn't that there was no theory of relativity, it was that there were two theories of relativity that were inconsistent. There was the old relativity of Galileo and Huygens from the early days of mechanics that said you could move by at a constant velocity, and indeed Newton's classical mechanics has that property. And there was the Lorentz-Poincaré relativity of the electromagnetic field theory. Lorentz and Poincaré had already developed the transformations that are now called Lorentz transformations and Poincaré transformations that tell you how to implement relativity, that is, invariance under boosts of the electromagnetic field equations of Maxwell. But these two relativities are inconsistent. The way they tell you to transform between space and time are not the same. Use different formulas. Einstein assumed the primacy of the electromagnetic relativity. So he was really putting the fields first, getting rid of the particles. It's ironic that therefore, I think, that it's widely thought that he was eliminating the ether. And I think it's because, in his mind, it was tied up with the problems that we now call quantum theory. He wanted to have photons coming in lumps. But logically, it's just topsy-turvy. We can see this on very general grounds, looking at special relativity. Special relativity introduces a limiting velocity, namely the speed of light, for the propagation of influence. That makes field theories almost inevitable. At least fields become very convenient, as you can see from this simple picture. If we try to make a theory of the interacting particles, so here are these world lines, and we want to know the forces or the influences that these different particles are feeling up here, if there's a limiting velocity, then the influence that this particle feels due to that one starts in the past over here. So we have to know where that particle used to be, not as in Newton's theory where it is now. And to get the total force, we have to know also the contributions from the other particles in their past at different times and add them all up in this very complicated way. So particle theory with the limiting velocity gets extremely complicated. A field theory tells us we should keep track of just the total disturbances at a given time, whereas the particle theory offers you the alternative of keeping track of all that stuff in the past. Of course, to get simple equations, we need to know the fields everywhere at one time, and then evolve them continuously. Because you just move each of these points a little bit, you can see that you're going to get simple equations by concentrating on the fields, the total fields everywhere at one time space. So the fields are at least extremely convenient. They're guaranteed to be extremely convenient, and even more so, the particle description is guaranteed to be extremely inconvenient if you have a limiting velocity. So, and the fields fill space if they're going to obey simple equations. In Maxwell's theory, they have a life of its own, their own. You can have electromagnetic waves, which aren't tied to particles. And so in those senses, they are definitely ethers. Of course, they're not mechanical ethers. They don't obey the Galileo-Newton relativity. You can't make them out of classical particles, but they obey electromagnetic relativity. There's absolutely no conflict between the idea of relativity and ethers. Quite the contrary. Relativity sort of forces you into fields. Do we really need them? As I said, Einstein hoped for a long time that you could get rid of them, perhaps until the day he died. They're convenient, but Einstein was famous for not caring about convenience. He wanted to be right in principle. And Feynman also thought so for a while. Feynman, of course, gave it up. And the reason he gave it up, he told me, is that when he went on to work further with his theory, he realized that it included processes like this, where you have the world lines of the particles folding in on themselves. And you see that it's no longer true that you can determine the electromagnetic influences solely by tracking what the particles were doing in the past. The fields, in this case the electron-positron field, have really taken on a life of their own. These processes can occur anywhere in space and time. And so empty space strikes back. It's not really empty, even in Feynman's formulation. And of course, he went on to prove that it is in fact equivalent mathematically to the field, to the standard field formulation. These tendencies for quantum fields to take on a life of their own reach a new level when we come to QCD and the colored gluons. In QCD, the influence of spontaneous activity in empty space is much more prominent than in QED. In QED, the vacuum polarizations typically a quantitatively quite small effect. In QCD, the vacuum polarization is a very big effect. It leads to asymptotic freedom, the fact that the interaction becomes weak at short distances or high energies, but becomes very, very strong at long distances or low energies. And to its flip side, at long distances, the confinement of quarks. So, if you wanted to write down a Feynman diagram description, say, of what a proton looks like, it doesn't just look like three particles moving around. You have net three quarks, but you have all kinds of quantum fluctuations of the gluon field, and these are quantitatively large because the coupling constant associated with these vertices is not small. You have to add up all these processes going on in space and time, with vacuum polarization, interaction among the gluons, and so forth. If you take any time slice, you'll notice that the proton is a very complicated object described in terms of particles. It has not only three quarks, but also arbitrary numbers of quark, anti-quark pairs, and gluons. In quantum mechanics, we have space-filling wave functions for the probability amplitudes of fields, of course, as in Schrodinger's equation. And we have n particles. The space becomes pretty big. The wave function doesn't live in ordinary space. It contains the possibility of correlations between the amplitudes of the different x's, of the positions of the different x's. So it's not just psi of x1 times another psi of x2 and so forth. It doesn't live in this direct sum space, which that kind of factorization would be. Instead, it lives in this so-called tensor product space, which is a space of 3n dimensions. You've probably heard in some colloquy here quibbling about whether space is 3-dimensional or 9-dimensional or maybe 10-dimensional. But the space of physics is actually very much larger than any of those numbers. For n particles, it's 3n dimensional space. Hilbert space really is, which is successfully used throughout physics, really is much larger than any piddling real space. When we go to fields, then we have a probability amplitude not for the positions of particles, but for the field amplitude at every point of space. And so we have a probability associated with every possible space field amplitude. This space can be thought, if you discretize the space, as r to the number of points in your discretization times 3. So if your discretization gets better and better, you get a closer and closer to approximation to r to the infinity. The real Hilbert space of quantum field theory is highly infinite dimensional. This means that to do accurate calculations, when field theory really is important, and quantum fluctuations really are important, we have to sample this enormous space of possibilities. And that's why lattice QCD taxes the resources of even the most advanced computers today, and the ingenuity of the people who use them. So it's hard work. But there's a payoff. One payoff is you actually get to compute from first principles things like the proton mass. But another payoff that's relevant now is that you get to see nice movies and pictures of what empty space looks like. It's full of these quantum fluctuations, and in the course of computing things like the proton mass, you have to get many, many samples. And so you get samples, snapshots of what empty space looks like, what the quantum fluctuations look like, what you would see if you dumped enough energy into small volumes to be able to discern those fluctuations. So here it comes. This is what your eyes would see if they could resolve distances of order 10 to the minus 14 centimeters and times of order 10 to the minus 24 seconds. Our eyes weren't evolved for that. It wouldn't be very helpful in avoiding predators or finding desirable mates or any of those things. But with our minds and with the help of the computers that are doing other successful calculations, we can see it. And here's what it looks like. So this is what your eyes would see if they could resolve times and distances that well. This is the actual calculation of the fluctuations in the color gluon fields. This is, for experts, this is their topological charge, but the energy density wouldn't look so different. This particular thing is about the size of a proton. This movie has the field smoothed out because otherwise it would be hard to make. There wouldn't be enough pixels to make it accurately. And it also, of course, has a finite loop. In fact, there are only 5 pictures in this loop. In reality, you wouldn't get it repeating, but it gives you the idea of that there are violent fluctuations going on all the time in empty space when we get to the basic field description. The fields really have taken on a life of their own in a big way. This is all vacuum polarization. The vacuum is polarized like crazy. Or another way to say it, there were no sources for any of that. That's just happening spontaneously. Somebody really likes that picture, I guess. Protests whenever it's not on. We've come a long way from the quark model, that protons are made out of just 3 quarks, and from, even more profoundly, from the traditional idea that matter is made out of hard, massy, impenetrable building blocks, the traditional picture that took its classical form from Newton. So here's the picture of a proton in the quark model. 3 quarks with some kind of force holding it together. Here's a small sample of the real thing. And the real thing has these fluctuating fields going crazy. And if you want to see what the force that the net force between quarks is, what you've got to do is compute those fluctuations, compute how they're modified when you put quarks in. So those were fluctuations in empty space. When you put in quarks, the fluctuations get modified. If you average over the fluctuations and just look at the net change, then you get this kind of picture, seeing that this is the disturbance in the fluctuations in the gluon fields, the energy in the net disturbance due to the presence of 3 quarks. And this is our deepest understanding of what holds a proton together. And when you calculate the mass in the computer, this is the sort of thing you calculate. So, instead of the traditional idea that matter is made out of some particles, the opposite point of view seems much more appropriate, certainly to protons. It's not that particles form fields, it's that fields are the primary objects. Protons, and by extension other forms of what we call matter, are excitations in the fields, which are the things that obey simple equations and the things that we actually calculate with. Besides these kinds of wildly fluctuating quantum mechanical ethers, or quantum fields, there's a set of much more material, substantial ethers that play a role in fundamental physics today. So, the notion of space being filled with things is even more concrete because we can tell what these things are and break pieces off and identify what made them. So, besides the fluctuating quantum fields, there are stable condensations, we call them, that fill space. The one that's best understood, by far, is the condensation called technically the chiral condensate of QCD. It's a condensate of quark and anti-quark pairs. If you really did empty out space, of course you can't empty it out of the quantum fluctuations, but if you emptied it out of actual particles and started with what we call the Fock space vacuum, you'd find that it's unstable. The force between quarks and antiquarks is so attractive that you can make a pair, which costs some energy, but then you gain so much energy from their attraction that there's a net gain. You can gain more from their attractive interaction, from them doing work on each other and coming together, than it costs to make them in the first place. So quark-antiquark pairs, in empty space, as empty as it could be, would have negative energy. That makes empty space unstable. That means it's advantageous to start making these pairs, and that's what'll happen. That's what does. If you make pairs and make pairs, it only stops when the repulsive forces between the pairs that are already there make the net energy balance no longer favorable. There's both numerical and extensive experimental evidence for this phenomenon. Numerically, we can calculate it from the equations of QCD that are so successful in many other applications, so we can believe it. Experimentally, many of the properties of pi mesons are best understood by picturing pi mesons as, in fact, oscillations of this quark-antiquark condensate. So, I didn't find a nice animation, but this is my hand-drawn graph of empty space. If you looked at it through eyes, I could see quark-antiquark pairs. These are not fluctuations. These are actual things floating out there, the chiral condensate. In the standard model of electroweak interactions, we need to postulate that empty space is a superconductor for the weak interaction. The primary equations, the symmetric equations of gauge theories, which are the basis of the electroweak theory, would predict that the gauge bosons are massless, just like photons, or for that matter, gravitons, or color gluons are massless. But of course, the gauge bosons of the weak interactions are observed not to be massless. They're the W and Z bosons, which definitely have mass. The only way we know how to implement that correction to the equations is to borrow a lesson from the theory of superconductivity. If you lived inside superconductor, you would think that photons had mass. Photons, in the superconductor, the electromagnetic interaction becomes short range. There's the Meissner effect, which says that magnetic fields can't penetrate very far, for example. So the idea, the primary idea, besides gauge theory, of our modern theory of electroweak interactions, is that empty space is a superconductor, not for electromagnetism, but for the currents that the W and Z boson care about, and that makes the W and Z bosons massive. We don't know exactly why empty space, unlike in the cases of quarks and antiquarks, where we know what it's made out of and know why this condensate forms, why we don't know for the weak interaction what makes empty space a superconductor. It's definitely not electrons, which is it is for ordinary superconductors, and it can't be identified with any known particle. None of the known particles has the right properties, or pairs of particles, or anything else. It's often blamed on a condensation of something called Higgs particles, but really that's just a parameterization of ignorance. We don't know, for instance, whether there's one Higgs particle or many Higgs particles. Whatever it is, Mr. Higgs gets a Nobel Prize, I guess, because whatever it is, it'll be called Higgs particles. But we don't know what it is. We do know that there's this superconductor. We think we know. We have a very successful theory based on that property of empty space being a superconductor for the W and Z boson currents, but we don't know what that really is concretely. We don't know whether there's one particle involved or several, or perhaps something more exotic. Building further on that idea, which was taken from superconductivity of metals, going one step further, we can postulate the existence of additional condensates if it's useful. And that turns out to be extremely useful in considering the possibility that we have even larger gauge symmetries of the world that combine the SU3 cross SU2 cross U1 of the standard model, which are separate symmetries within the standard model, into an overarching symmetry. That would predict even more massless gauge bosons. We need more kinds of superconductors to get rid of those. In fact, we need them to make them much heavier than the W and Z bosons because they haven't been seen. And not only haven't they been seen, but they mediate things like proton decay, which are known to happen very, very rarely. So they've got to be made very heavy. You can do it. With the stroke of a pen, you can implement the equations of this superconductivity. And you find that it has very beneficial effects. This is a different colloquium. I won't have time to do justice to this. But if you assume that the primary equations are fully symmetric, you can follow out the effect of having the superconductor make some gauge bosons heavy and others not, breaking the symmetry. That means the vacuum polarization felt by the different interactions are different, no longer symmetric, and then you can calculate the effect of those vacuum polarizations to see if they give a consistent fit of the observed strength of the interactions we see based on a unified description at some much shorter distance where the superconducting currents haven't yet screened the charge. And that works beautifully if you include supersymmetry, and gravity fits too, but I won't have time to describe all this in detail. Just take my word for it. If you assume that empty space is a multi-layered, multicolored superconductor, you can make progress in understanding the world. Not only in the weak interactions, but well beyond the standard model. Yet another ether is the one that convinced Einstein, the metric that he introduced, for that matter. That's probably why he found it convincing. The metric ether of space-time. In general relativity, space-time is dynamical. It can bend and oscillate. In fact, that's, in some sense, the origin of gravity. Masses, or more precisely, distributions of energy and momentum bend space-time, and that affects how other distributions of energy and momentum travel. That's how general relativity interprets gravity. This dynamics can be represented by a space-time metric field, g mu nu. In fact, the x's that appear here could parameterize a perfectly flat space, and if you have instructions for how to patch the directions and lengths together, which are given by this g mu nu, a field in flat space, or a field whose based on coordinates that have no spatial interpretation, becomes something that describes a curved spacetime. The metric field is usually taken to be fundamental. This is what Einstein said. For these confer upon space its metrical qualities without which it cannot be imagined at all. But in many ways, it resembles the kind of material condensates we talked about in terms of quark-antiquark condensates, or the superconducting condensates of electroweak theory and unified interactions. Specifically, it breaks symmetry. For experts, the symmetry it breaks is the following. If we didn't have a metric field, then we have true general covariance. That is, we could transform the x's in any way we wanted to, and it wouldn't change physics. If we put in the metric field, that's not the case. What's usually called general covariance in general relativity requires that when you change the x's, you also change the g's in a very particular way. So it's not the case that you just can use any coordinate system equally well. You can use different coordinate systems if at the same time you adjust the g's. So if there were no g's, we'd have more symmetry. You wouldn't have to adjust anything. Well, this is a more refined version for experts, but I better skip it in view of the time. So it breaks symmetry, like those other material condensates, and it also has complicated couplings. The Lagrangian, if you like, for general relativity is considerably more complicated than the Lagrangian for the other theories that make up our current fundamental understanding of physics. In particular, it's non-polynomial. It has this square, very funny square root of g, and so forth. It appears, for experts realize that it much more resembles a nonlinear sigma model, which in turn is something that usually is meant to describe symmetry-breaking condensate or order parameter in a complicated system. One can carry that thought considerably further, and if you want to travel to Uppsala in a couple of weeks, I'll be giving a seminar on it. The most dramatic, however, demonstration of the reality of ether, if you like, that's really hard to deny, is the recent discovery that ether weighs. Having weight, that is, having mass, is almost the definition of what it means to be substantial. Hard to push around. How could we recognize that it's ether that's weighing and not a bunch of particles? Well, ether weight has a very particular property. When you have a density due to ether, it should have also associated with the pressure. Maybe I should step back a little bit. If you have a density that's associated with ether, the first property that it should have is that it should be the same everywhere and also the same for all time. It's going to be an intrinsic property of space-time. But then a second quality it should have is that it should have pressure associated with it according to this equation, P equals minus rho times C squared. Let me explain that a bit. This equation looks like E equals mc squared, but it's kind of a mutant version. Right? With rho is kind of a mass, pressure is kind of an energy, but then there's also this minus sign. Looks funny. It's actually very, very closely related to E equals mc squared. Let me explain that a second. So, if the density of ether, the density of empty space, is going to stay constant as the universe expands, something funny has to happen. Ordinary matter, of course, as the universe expands, gets more diluted. Density goes down. How can you have something that has a constant density even though it's filling a bigger and bigger volume? Well, ordinary pressure would mean that you do work as you expand against it. And so you have to lose additional energy to work. Negative pressure, which is what you get according to this equation, means that as the universe expands, as your little volume element expands, work is done on you by the negative pressure. And if you compute the amount of work done, PdV, the amount of energy you gain, and demand that it matches rho dV divided by c squared, the change in mass, the change in energy, rho dV times c squared, the change in energy, you'll find that they match if and only if the negative pressure is equal to rho c squared. So this is the necessary relationship that determines that density will be conserved. It's also closely related to the special relativistic invariance of this ether. Namely, if you moved past empty space at apparently empty space at a finite velocity, you would think that the density would increase because of the Lorentz-Fitzgerald contraction. One of the directions gets contracted, it would seem that the density has to increase because it's the same thing filling a smaller volume. However, the relativistic transformation laws for density are related to pressure, roughly similar to the way relativistic transformation laws relate space and time. They get mixed up. Density and pressure also get mixed up. And if you have precisely this relationship, both stay the same. Both are measured at the same values according to moving observers. And consistent with that, it's also the relation you get for scalar condensates, such as the condensate of quark-antiquark pairs, or any of these things that are supposed to make superconductors for the weak interactions or unified interactions. Here are sensible estimates for the amount of density you get with from those different contributions. So, for the quark-antiquark condensate, you get about 10 to the 44th times what's observed. For the weak superconducting condensate, you get about 10 to the 56th times what's observed. For the unified superconducting condensate, you get about 112 times, 10 to the 112 times what's observed. For quantum fluctuations, well, if you don't have supersymmetry, it's just infinite, the amount of zero-point energy. If you have supersymmetry, the situation is much better. It's only 10 to the 60 orders of magnitude bigger than observed. So, given these naive estimates that the density of empty space should be much, much larger than what's observed, most theorists predicted that the actual density would be zero. That there was some profound principle missing that would tell you that it's much, much smaller than it should be because it's actually zero. That was Feynman's idea. He wanted to make space empty. And maybe that's the right answer. Oh. But astronomers discovered something different recently. They were looking at the expansion of the universe, expecting that the rate of expansion would slow down. We'll go back. And it did for a while. But then, fairly recently, it started accelerating again. And the only way that we know how to explain that is that on cosmological scales there's this negative pressure that adds up and causes the universe to accelerate its expansion, taking advantage of the space doing work on it as it goes out, to counteract the universal effect of gravity, which would also always be to slow down the expansion. So apparently it's not zero. That is, we need the negative pressure. Quite independently and by different techniques, you can also measure the density of different things in the universe and the total density, and you find that there's a missing bit that seems to be very uniformly distributed and to satisfy exactly this equation, rho equals minus pc squared. Also, it's worth noting that a much larger value of minus p is postulated to drive inflation in the very early universe. So, insofar as inflation is successful, it gives another indication of the weight of empty space, or the reality of ether. So let me summarize and suggest that we get rid of ether, the word ether, not ether, but the word ether, in favor of something more modern and sexy. So, to summarize, I'll need a lot of space on this. The primary structure of physical reality, the primary ingredient out of which we build our physical theories, is something that fills space, is full of quantum activity. Quantum activity means that it's spontaneous, unpredictable, and that you have to look to see it. We've illustrated all those properties. It has material components as well as these funny quantum fluctuating components, things that are material by almost any standard. It also has metric components that may be material. And finally, it also weighs. The archaic word ether does not do justice to this structure. People didn't dream of the quantum fluctuations, or that the luminiferous ether would weigh anything, and so forth. Nor really does quantum field. Quantum field does justice to the spontaneous activity, but not to the other aspects. A better and more timely metaphor is the grid. This grid is sort of the scientific descriptive grid. Here's space, and you see what really is in space can be described in terms of different parameters that tell you what's there. So if we instead went a level deeper and said the quark and gluon fields, the condensates, the metric field, and the density, that would be a proper description of physical reality of those grids. When we actually compute, you'll notice in the background here, there's a computational grid. That's how the computations are actually done in a computer. It sets up a numerical grid replacing space-time by points. And what makes it especially timely, I think, is that now a grid that's sort of a worthy metaphor for our physical grid is being built. This is the next step beyond the World Wide Web, hooking up computers all over the world into one gigantic, powerful computing machine whose power you can tap into from any node on it. So I think grid is a good thing to replace ether. Whatever you call it, though, I hope I've shown you that reality is full. Full in many ways. Now, to close, I'll answer questions, but I'll also put up in background a fantasy grid that I found in my explorations on the web that's really quite hypnotic. I hope it doesn't distract you from asking questions. But in any case, here it comes. All right, thank you very much.
So we have time for some questions. Anyone who's going to ask something? Yes, please.
I have a more historical problem terms. It's not so related to the introduction perhaps about Einstein's attitudes towards the ether.
Yes.
For instance, you said that especially with heat story reproduces in ether. But I think that what really bothered Einstein was that not the space-faring quality of the mechanical ether, but the fact that it was considered to be the absolute stress strain. So in electrodynamics,
yes.
From Maxwell and Laureate, you have
Yes.
one frame where Maxwell's equations are valid and the rest of the...
Yeah. Well, if he had just said that we have these space-filling things, the electric and magnetic fields, but they don't define a stationary rest frame, then that would have been one thing, and that's sort of what I would have expected for the intellect. That's not what he said. He said that there's nothing there, and I think the reason is that he really wanted to get rid of it. He wanted to get rid of the electric and magnetic fields as independent objects to just have excitations concentrated in little lumps. He really took photons seriously. That's what I get from the reading.
Then I have to go to the next talk that you gave in Salzburg. If you read that paper, you see that he is discussing the operations in the radiation pressure.
Yes.
Two terms, one which is what and one is radiation.
Yes.
What like the expression he identifies with photons.
Yes.
And then of course he had the Maxwell field. And your quotation here was from the very end of that paper where it
Yes.
says that, okay, how can we understand both particles and waves? Well, this is a suggestion. Perhaps
Yes.
you can see it as
Yes.
similarity.
That's right.
So I don't think you should interpret him literally what he actually meant. He was concerned about having both of these things that wasn't trying to throw out any
Well, look, the last thing I want to do is try to besmirch Einstein's reputation. And that's, I mean, I couldn't do that anyway, even if I wanted to, which I don't. I'm trying to understand how he could have expressed himself so strongly in a way that I find quite paradoxical. I mean, really what he was doing was promoting the field-inspired relativity above the traditional mechanical relativity when you have this conflict between the two. So I would have thought that an appropriate way to say it was, wow, the fields really are fundamental, right? And we have to modify mechanics, and this is what you get. And it's not that we don't have an ether, it's that the ether looks the same if you move past it at a finite velocity. That's how I would have said it. But of course, Einstein said it. I didn't understand why Einstein didn't say it that way, and now I think it's because he had these doubts in his mind because of exactly these kinds of problems about photons and radiation pressure problems.
Frank has literally had to fly away, so I would like the questions to be short. Please, Josta.
the answers to
I
it.
think my comment is already done.
Excuse me?
You had a question.
I had a question. Your talk seemed to explain almost everything. In particular, I think the cosmological constant was what you referred to there.
Yeah.
What about dark matter? You didn't mention that. What is it?
Well, those are excitations in some other ether. We don't know what it is.
But you don't like the whole theory.
That's another talk. I mean, I mean, their leading
No
candidates
theory.
are something to do with supersymmetry or axions, but they're more conventional. I mean, that's a much more conventional form of matter. It seems not to have negative pressure. It seems to be clumpy. It doesn't, so it seems to be excitations that you get from much more conventional sources, not a material that fills all space and time.
Yes, please.
Yeah, you showed an animation of fluctuations, but in reality, what is it that sets the time scale for fluctuations?
Well, ultimately, it would be the QCD coupling constant. Yeah. And, well, yeah, it's also, well, that actually more sets the density. The time scale is the speed of light. So it depends on what distance you're looking. But,
As we all know, Frank is staying with us for some time, so I think we have enough.
no, well,
You want to
One
add
more,
some
one more.
then. Yes.
Yeah, sorry. At the time, the old notion of ether was also responsible for, I mean, kind of something responsible for absolute space. Now, this set.
yeah,
In addition to, I mean, just filling that
Yes.
space, helping you fill all this.
that's
So,
right.
for this, in this modern, I mean, concept for ether, this is not true, right? I mean, this is a different.
The modern ether looks the same if you move past it at a finite velocity. So it obeys electromagnetic relativity. It
But
obeys
it's the same for all the observers, right?
the same for all the observers.
So it's
right?
different with the, I mean,
It's different from what you would have had in mind if you had in mind a ether that obeyed mechanical relativity. Right? But it's exactly what you have in mind if you want empty space to obey electromagnetic relativity, which, after all, electromagnetism is something that the electric and magnetic fields are these things that fill all space, that have their own physical reality, that are fluctuating all the time. But it's just because this word ether carries so much baggage and has such a bad reputation that I think we need a new word.
Okay, I think, thank you.